The second speak is by Dr. David Rowlands. I invited David to give the presentation.
Well, thank you so much. It would be perhaps at first, it will be myself and then my colleague, Dr. David Rowland. I will pass on the presentation to Dr. David Rowland to continue.
Okay.
Well, once again, thank you so much for the opportunity. First of all, just an introduction about myself. My name is Sanam Aghdamy, and I received my PhD from Queensland University of Technology, QUT, on dynamic responsive structure. I was a research fellow there, and in 2019, I joined School of Engineering and Built Environment at Griffith University. A little background on what I'm presenting today. In 2018, our School of Engineering and Built Environment decided to design our new academic building, which we call it N79, as a living laboratory to leverage access to the live and big data, enabling structural health monitoring, as well as to scaffold the digital literacy for our Griffith University students. So as a part of that, a team has been developed. We call it N79 Living Laboratory team. As you can see here, Dr. Dominic Ong is the subsurface lead. Dr. Guna Gunalan is the above the ground lead. Dr. David Rowland is the member in software engineering. Professor Hong Guan is the member in structural engineering. Dr. Andy Yuan is our USQ collaborator, and we are very thankful to him for his support. We have Associate Professor Cheryl Deshaw as the N79 end user coordinator, and it would be myself as the project coordinator, as well as the above the ground lead. As you know, this is a huge project involving a few sub-projects, and one of these sub-projects is how do we deal with huge live data? How do we manage that? And how to be able to safely acquire, store, and visualize the data, which enables the structural health monitoring research studies. So that team involves Mr. Zane Keeley, which is our Griffith University students, Dr. David Rowland as a software engineering, myself, and Dr. Dominic Ong as the structural and geotechnical academic involved. We also collaborating with our industry partner, the Urban Institute, which is the data analytic company and incubator and innovator of software in the field of smart cities. So perhaps now it's clear that what I'm presenting today, it's basically a narrative on what we experienced as a team in developing the dashboard and also managing the data, enabling structural health monitoring. That's the outline of the presentation. I will cover the first part, the introduction, and also the specification of the sensors and the location of them. And then I will pass on the presentation to my colleague, Dr. David Rowland, who would explain about the system design, software design, and data retrieval software module, and dashboard design, and finally system testing. And hopefully at the end of this presentation, we can provide and share some of the guidelines and experiences that we have in developing a dashboard. We know that few universities, including, we've got Curtin University, University of Melbourne, and other universities have started having the living laboratory. And hopefully that would be a guideline for others who would like to develop the living laboratories and developing an in-house dashboard. Sorry, I will do this. So in 2016, our Griffith University Council agreed to add a new building to the Nathan campus. And in 2017, November 2017, the site establishment was started. And May 2018, the building construction commenced. And finally, in October 2019, the building construction completed. It was about May 2018 that the School of Engineering Built Environment decided to pursue the living laboratory outcome, and that's basically where the team formed. There are 7 aspects to this complex project. The first part is basically the benchmarking with other universities, including Curtin University, put it as QUT/USQ. We were talking to Dr. Andy Ewan, and he helped us a lot, and also University of Melbourne. The next phase was the selection of the sensors and installation of the sensors, finding the best location for the sensors, and then capturing those data. And the next phase for us was the management of this huge pool of data and development of the dashboard. And that's basically what's going to be mainly presented today. In the next phase, we've got the AR, artificial intelligence, augmented reality and virtual reality of N79, where the researcher and the students would be able to walk through the building, a virtual building, looking at the different sensors, finding the specification of the sensors, and finding the historical and live data of that particular sensor. In the last, next to the last phase, we've got a digital twin development that has two parts to that. One would be in collaboration with Bentley and Siemens software. And then the other one is basically what we usually do for structural health monitoring. And that's the development of the finite element model, predicted the behavior of the building, and then using the sensor data to update the model. And finally, use all this to basically conduct the research studies and also integrating those into the curriculum of engineering students. A little bit of information about the sensors that we've got under the ground. Perhaps I'll show it here. We've got vibrating wire earth pressure cells. We've got 7 of those that are installed on the 5 footing, and that's to measure the bearing pressure of the founding material. And that's basically showing the installation of those sensors. We also got vibrating wire piezometers as well as the observation well. These are to measure and monitor the water table fluctuations. If you look here, that's the N79 building. They are immediately across the road. There's one vibrating wire piezometer that is installed here, and then the other one is over here. And then we've got the observation well. And that's basically showing how we installed these sensors. Apart from the underground sensors, we do have the sensors above the ground. One of those is the weather station, and that weather station obviously is installed on the N79 rooftop, and that's to monitor the standard environmental variables, including the relative humidity, air temperature, wind velocity, and etc. Apart from that, we've got the 2 accelerometers that are mainly to monitor the health of the structure, is mainly the global behavior. They are installed on level 1, 3, and 5. So basically, they are installed on level 1, level 3, and level 5 of the building. This is a 6-story building, but unfortunately, one of these columns is discontinued to level 6. That's why we couldn't have the sensors there. We installed the sensors on level 5. It's not a rectangular plan. It's not a rectangular building. It's a semi-rectangular, and that's why we've got the sensors installed on 3 main corners. These are single-axis accelerometers on this particular corner of the building. We've got 2 accelerometers, one measuring in X direction, and then the other one is in Y direction. And then we've got single-axis accelerometers installed at this corner and this corner of the building. One of them is measuring in Y direction, and then the other one is measuring in X direction. Sorry about that. We also got 15 strain gauges. These are basically to measure the local behavior of the structure, including the deflection due to the crane rollover, including concrete creep and shrinkage, structural vibration induced by people movement or machineries, and finally deflection due to the wind gust. All the strain gauges are installed on level 1 of the building. And I believe that's all about the specification of sensors and the location of the sensors. I'll pass on the presentation to my colleague, Dr. David Rowlands, who would explain about the data management and development of the dashboard. Thank you so much.
Okay, my apologies. I won't be a second. I'm just going to share my screen. And I'm aware that we're running very short of time as well. Okay, thank you, Sanam. Thank you, everybody. My name's David Rowlands. Extensively, I'm a software engineer and electronic engineer with the School of Engineering. And as part of a final year project, we got a student, Zane, Keeley, to work with us. And this is a very beneficial situation because in the design and work of everything here, there are a lot of great learning opportunities for our students. And particularly so they can see that things work and don't work. Okay, so to rush through the details here, we know we're going to have about 30 sensors. We want to get it to pass data in real time. It means we're going to have to capture, store and display it. In order to do that, we're going to have to think carefully about the data infrastructure and basically data formats between devices. Okay, so it sounds a very simple task, but it's not quite as simple to work with in real life. Okay, so our following slides will present. Okay, so basically the system design is the university already had a data storage system that they used to store information about the power and temperatures and things like that and other buildings. And that was a OSI Pi system, PiSoft. Last year, as presented by Sanam, the vibrating wire piezometers and the earth pressure cells were coming through, stored in the PI system, okay, of which we could use their dedicated software to pull out in their APIs. After that system had been set up, the accelerometers and strain gauges were starting to be applied to the building. The accelerometers basically came out and gave a signal, an analog signal that had to be converted to digital. And we did that through something known as a CDAC, which is a box by National Instruments. So we had to convert that data into something usable. And then at the end, we wanted to create an informational dashboard. So in order to create that informational dashboard, we were going to need a framework to do that. And that's where the Urban Institute came in. They basically work with a smart data system that they've created, which is sitting around the KX system. So they basically have a KX server there. And our whole idea was we will collect the data from the various sensors, convert it into a format, get it to the KX system. The KX system will then store it in its database, okay, its live or short-term database and its long-term database, and then we can extract the data from that directly using the tools already existing in the KX subsystem to enable us to display useful dashboards. So the immediate thing that we came across was that we had two disparate systems. Okay, so the KX will be running elsewhere. For this project done by the student, we set it up just in a Linux box in the building. We had to be able to extract the data, and then we had to be able to communicate the data from the PiSoft. We had to extract the data from the strain gauges and accelerometer, and also transmit that to the KSoft server. So the easiest methodology that we found to do that was to use the CSV files because the comma delimited is the most standard format. It's not the most efficient, because you have to represent each of the numbers by actually ASCII digits. It's much better to do it digitally, but simply, there was a very simple method that we could use. We know that the PySoft system very easily handles the CSV files. On our accelerometer side, we had to convert the data into a CSV file, okay? And then our communication software will take the data from the CSV files and send them through to the web server, the KX server. And we do that using WebSockets because that will have a persistent communication. And it's like opening up a separate channel that we can pass our data through. Okay, so in the software design, it was basically designed around those 4 modules: a data retrieval, a PySoft system, which allows us to interrogate, data communication module, and the KX server module. So to give you an idea of the structure of those, we had to write the software to allow us to extract the data, in particular from the NIDAC system, where the accelerometers and the strain gauges would be connected. We found we had to convert the data to CSV. So we had to find some way to communicate to that box, extract the data from the box, and then put it in a format for another system. So already you can see there are these multiple hops. And that's one of the things we've got to watch out for when we're putting together a data system is how much translation do we need? How many separate aggregators do we need? Because on a larger system, that can make it get very complex very quickly. So basically, we would retrieve the sensor data by sending the command to the NIDAC, generate timestamps. If we need to calculate some derived outputs, we could do it here. We could even do some calibration adjustments here as we needed to, and just store it within a CSV file. With the Pi system, we request the data, we'll process it in whatever way we need to, like a bit of a post-processing, and then store it into the CSV. Now, the way this worked was we did this as a straight spool type system. So as a spooler, you have a directory, you drop files in, that directory will be checked on a regular basis. If there's something in there, then the thread or the process will pick that up and act upon it and send the data accordingly. So that's where the data communication module comes in, checks the spool directory. If it doesn't find, it keeps checking. Mind you, we don't do that on a continual basis because that would load the system right down. We check on a regular basis. So if we found it, we'll read the data from the CSV. Then we have to put it into the WebSockets. By putting it into the WebSocket format, we're basically packetizing that data. We want to make sure we get an efficient use of the packets. We don't want lots of half-empty packets.
So bad.
Time? Okay. All right. So basically, we were running the KX software here. And we're pulling the database, putting the information into the database, pulling the information out of the database. The dashboard design, it's important to minimize the number of visualizations that you've got. If it's important and to be emphasized, increase the space. And basically, when you're developing, obtain the feedback for each iteration. We had some constraints of the software, and that's always a problem with the system. So just to show you a quick example of one of the dashboards, we have some data. This is mocked up data, but it's using the system. We will show something to show where the sensors are. We can set thresholds. We can select a time. We can select a date, and we will have accelerometer choice for each of the various colors that we'll step through. The other advantage is in the system that we have, we can pull down an Excel spreadsheet with the tables in. We have our Excel, we have another version where we have a table in as well, which will be good for students and researchers to access the data. We did some load testing to make sure that we weren't overloading the system. So very briefly, I'll probably take about a minute or so. Apologies for my rushing, but basically, things we need to really think about was identify the stakeholders and their needs. Okay, make sure you're aware of the different roles, because you have researchers, you have students, you have academics, you have the people who are running the university infrastructure. Okay, so you need to be very, very clear of what you want out of the system and who's going to be part of it, because you need to be able to take all of those into account. When you're working with the data, particularly when you're planning and designing, understand what the data is, what bandwidth you need, how many samples per second are you requiring, what is the data resolution and the range, the number of samples, because all of these quickly add up to increase the size of the data that you actually have to send. If it's on a real-time thing, be aware that items can go down. So what can you afford to lose? You're going to be storing it for a long, long time. If you want historical data, that takes space. And of course, there's a cost with storing in long time. Okay, I really think we ran into where we had a couple of different systems. I think it would, if possible, simplify where you can and unify the infrastructure. Okay, if you can do that, it makes it much easier to keep adding. I want to point out that this whole system is a multidisciplinary task. You have software engineers, you have software managers, you have system managers within the universities, you have engineers, you have structural engineers and so on. It's good to get them involved early so that you can make sure that you get, you know, the simplest system that people can work with. And don't forget, you've really got to think about troubleshooting. Okay, someone has to maintain that system. So that's why it's good to get everybody there in the first instance. And the last thing I want to say, and it's a very important point, keep the dashboard simple, but don't make it too simple. You still got to get information across. So keep it simple, but just don't dumb down the data. Thank you.
Okay, thanks, Zane and David, for the comprehensive presentation. It's a great project. At concerned time, maybe the audience could use the chat box for the questions.
Okay.
Okay. Okay. You have to move to the third presentation.